Hi guys, it's Kristen from Kristen Moon Science. I'm hopping on because a friend and follower has asked for help in explaining valence electrons, the octet rule, and Lewis structures. She teaches in a co-op setting and finds that the 1 hour class time per week is just not enough time to fit it all in, and so she's looking for a way to present the material concisely and in a way her kids will understand. So I'm making this video to help her out and thought I'd share it here too in case it will help you out. So I've shared before on my site how valuable I find having a large copy of the periodic table available to students. Even if you're just teaching a single student at home, having a large version of the periodic table on the wall for students to look at while they're learning is just very helpful. It's just a lot easier for them to work with than having to flip back and forth to the copy that they have in their textbook. And the periodic table is not just some random assortment of letters on the wall. You can actually glean a lot of information, and I want to talk to you about that. So I've kind of cut and pasted some, just a portion of the periodic table to show you. So you probably have noticed, and your students have noticed, that the elements are always displayed in a certain way on the periodic table, and they are listed by number. So hydrogen is 1, helium is 2, lithium is 3, beryllium is 4, and so on and so forth. Well, those numbers are not arbitrary. Those are called the atomic numbers of the element, and they actually serve a purpose. They tell you something about each of the elements. So let's look at helium. Helium has an atomic number of 2, lithium, atomic number of 3, so on and so forth. That atomic number actually corresponds to the number of protons that that element has. So helium with the atomic number of 2 has 2 protons. Lithium with the atomic number of 3 has 3 protons. Boron with the atomic number of 5 has 5 protons. Magnesium with atomic number of 12 has 12 protons, and so on and so forth. So just by looking at the periodic table and seeing what the element's atomic number is, you've automatically peeked inside that element and you know how many protons an atom of that element has. You can learn even more because in its natural state, an atom or an element is electrically neutral. So protons have a positive charge. So 2 protons would be an electrical charge of positive 2. 3 protons would be a positive charge of 3. But in order for the atom to be atomically neutral, electrically neutral, it must have something to balance out that positive charge. And the thing in an atom that balances out the positive charge are the negatively charged electrons. So back up. So for helium to have a positive charge of 2, in order to be electrically neutral, it must have 2 electrons. And it turns out it does. So helium has 2 protons and 2 electrons. And you were able to figure that out because you know that helium has an atomic number of 2. So lithium, if it has 3 protons with a positive charge, it must have 3 electrons with a negative 3 charge. So the positive 3 and the negative 3 cancel each other out. So a lithium atom in its natural state will be electrically neutral. So if boron has 5 protons, which you can tell because it has an atomic number of 5, you can automatically conclude that it also has 5 electrons, which it does. And magnesium with 12 protons, 12 electrons. And that's true, okay? So just by looking at the periodic table, you can tell how many protons and how many electrons an atom in its natural state will have. So when we're talking about electrons, it's important to know that not all of an atom's electrons live in the same place. And of course they don't live, but this is just how I like to explain things to my students. So if I use vernacular like that, I hope you understand that I know that atoms are not alive. Okay, so not all of an atom's electrons live in the same place. It turns out that different electrons have different amounts of energy. And electrons that have the same amount of energy do live in the same energy level. So different atoms have different energy levels. So let's think about carbon. So carbon has an atomic number of 6, which we just learned means it has 6 protons. And since we know it has 6 protons, we also know it has 6 electrons. Okay? Not all of those electrons, not all of those 6 electrons live in the same place. As your students are going through their chemistry class, they're going to learn about this. So before they get to Lewis structures, they're already familiar with this. Okay, so we're going to learn that when you're building an electron, or when you're building an atom using its electrons, the first 2 electrons go in the first energy level, and then that's all the room that energy level has. So that energy level is full. And then then the remaining electrons go in the next energy level. So the 6 electrons of carbon, 2 of them go in the first energy level, and the remaining 4 go in the second energy level. When atoms interact, it turns out that atoms are mainly empty space, okay? And when atoms interact, only the electrons in their outermost energy level are able to interact with other elements. Those are the only ones that come near other elements. So let's go back to that carbon. Carbon, we said it has 6 protons, 6 electrons. We saw our picture. 2 of those electrons are in the center. Only 4 of those electrons are in the outermost energy level. It's those 4 electrons that are going to be involved in all of the chemical reactions that take place with carbon. And we give the electrons that are in the outermost energy level a special name, and we call those valence electrons. So carbon has 4 valence electrons. It's those 4 valence electrons that participate in the chemical reactions that happen with carbon. Okay, I already said that. Valence electrons. Okay. We already said that. Carbon has 4. So then I just wanted to hop on and say this one thing. I've talked about PhET before. PhET is a website that has awesome free simulations that are kind of in a game-like format to allow your students the chance to play around with different things in math and science. And I really find these simulations helpful in chemistry in particular, because it's just really hard sometimes to visualize atoms. So I just wanted to remind you guys to go to PhET, to play around with their chemistry simulations. In one of the simulations, they are able to build atoms and see for themselves where the protons, where the neutrons, and where the electrons of atoms exist, and they can build them and they can see the valence electrons themselves. Okay, hopping back. So, talking about valence electrons, you can actually use the periodic table to figure out how many valence electrons an element has. Okay, so jumping back to a copy of the periodic table. See these numbers up here? The 1A, 2A, 3A, so on and so forth? Those numbers actually allow you to know how many valence electrons each of the elements in that column have. So all of the elements in column 1A have 1 valence electron. All the elements in column 2A have 2 valence electrons. Forget about the stuff in the middle for now. I just want to talk about basics in this video. The stuff in the middle and the stuff at the bottom, they don't play by neat and tidy rules, but we're going to talk about the ones that do follow the rules right now. So all of these guys in column 3A have 3 valence electrons. These guys have 4 valence electrons, 5 valence electrons, 6 valence electrons, 7 valence electrons, 8 valence electrons. So once again, periodic table saves the day. So much information, okay? So moving on from valence electrons to talking about Lewis structures. Lewis structures are a way to designate the number of valence electrons an element has and then visualize them so that you can understand what's going on in a chemical reaction. So this is what valence electrons look like. So lithium is in this 1A column, which means it has 1 valence electron, which we show with a single dot, okay? When we're talking about Lewis structures, we're only drawing pictures of the valence electrons, not all of the electrons an element has, just the ones that are in the outermost energy level, because it's those electrons that are going to participate in chemical reactions. Okay, so beryllium is in column 2A, which means it has 2 valence electrons, which we draw 1, 2. Boron has 3, 1, 2, 3. Carbon has 1, 2, 3, 4. Okay, so you do the first level first. You do 1, and then 2, and then 3, and then 4. And then if there's 5, then you start going around the circle again. So nitrogen has 5 valence electrons, so is 5. Oxygen has 6. Fluorine has 7. And neon has 8. So we'll come back to this in a minute. Neon is a noble gas. It has 8 valence electrons. All of its outer energy level is full of electrons. It can fit no more in on that energy level. And this is actually something that all the elements strive to attain. I call that Electron Nirvana. Once an element gets a full energy level in its outermost slot, it's perfectly happy and content. So that's how you draw valence electrons. So now we're going to talk about the octet rule. And I draw the octopus because in class I talk about, octet means 8, just like an octopus has 8 legs. So sometimes giving a silly visual helps people to understand. So there you go. Okay, so what is the octet rule? An atom is the most stable when it has a full outer energy level, which in this case means it has 8 electrons, 8 valence electrons, 8 electrons in its outer energy level. It's happy. And so consider the noble gases. The noble gases all have a full outer energy level. They all have 8 electrons, 8 valence electrons. They're full. They're happy. They are content. In fact, that's why they're called noble gases. Thinking back to the Middle Ages and the nobles, and they didn't interact with the commoners, right? They walked around with their noses up in the air, and they didn't want to associate with the lower classes because, they were so high and mighty. Okay, well, that's how we have named the noble gases. They actually were some of the last elements to be discovered on the periodic table because they don't interact. And they don't interact because they don't need to. They are fully content. They have a full energy level in their outer level. They are happy and they are content. But all other elements strive to get that octet, to get those 8 electrons in their outer level. They want to get that. They want to be like a noble gas. So basically all chemical reactions, all the reactions that your students will be studying in chemistry, all those chemical reactions take place because atoms are jockeying with electrons to try to get that perfect octet in their outer energy level. Okay, so we're getting to the end, okay? Lewis structures, one really cool thing about Lewis structures is that they can help us and our students visualize an atom's valence electrons and understand why chemical reactions occur the way they occur, okay? So consider sodium and chlorine. Now, I don't have the periodic table on this slide because I don't want it to be too messy, but you can take my word for it. Sodium is in that column 1A, which means it has 1 valence electron. Chlorine is in column 7A, which means it has 7 valence electrons. And when I'm doing Lewis structures with 2 different elements that are going to combine, I like to color them different ways. And my students actually like it too. When I'm teaching this in a co-op setting, when I know we're going to be talking about this, I encourage them to bring colored pencils to class so that they can color the electrons of different elements, different colors, which will just help them watch what happens to the different electrons as the elements interact. Okay, so sodium has 1 valence electron. It wants to get to 8. Chlorine has 7 valence electrons. It too wants to get to 8. These 2 things are going to interact, sodium and chlorine. So you have to think, what's going to happen? Is it easier? So you probably already know that an element, it can gain and lose electrons. Of all the things in an atom, the electrons are the most mobile. They can jump and hop and all kinds of things. So both sodium and chlorine want to have 8 valence electrons. Let's think about chlorine. Is it going to be easier for chlorine to lose 7 electrons, or do you think it's going to be easier for chlorine to steal 1 electron from something else? I think it's going to be easier for chlorine to steal, right? And think about sodium. Sodium only has 1 valence electron. Do you think it's going to be easier for sodium to steal 7 electrons from a different element? Or do you think it's going to be easier for sodium to get rid of that 1 valence electron? Because guess what? If it gets rid of that 1 valence electron in its outermost shell, beneath that outermost shell is another shell of a lower energy level that is full. So I think sodium is going to want to get rid of that extra valence electron. And it turns out that's what happens. All these things are happening. Anyway, my presentation isn't perfect, but anyway. So what's going to happen is that chlorine is going to steal the valence electron from sodium. And sodium is going to be happy to get rid of it, okay? So that's what actually happens. Chlorine steals that valence electron. Now, all of a sudden, chlorine has a full, complete set. It's got 8 valence electrons and it's happy. Sodium has lost its valence electron, but it's okay because now it's stable too. But because it now has sodium now has 1 more positive charged proton than it does electrons, it has a net electrical charge of +1. Chlorine, now that it has 1 extra electron, 1 more electron than it does proton, it has a net electrical charge of -1. And the positive charge and the negative charge, just like magnets, opposite sides of a magnet are attracted to each other. Opposite charges attract. So that negative charge of chlorine and the positive charge of sodium are going to interact with each other, and they will actually form an ionic bond and form sodium chloride. So actually, this is what it looks like. This is the chemical formula. That sodium with its net +1 charge and chlorine with its -1 charge will form together to form sodium chloride, which you and I both know and love as table salt. Okay? So the Lewis structures, once your kids get the hang of them, they will be able to visualize the valence electrons, and by visualizing them, they will be able to understand why 2 different elements interact, how they interact, and so on and so forth. Okay? I'm going to show you one more thing, and then I'll be done. So once again, in this one, we've got chlorine. We've already talked about chlorine is in row 7A of the periodic table, so it has 7 valence electrons. But magnesium is in column 2A. It has 2 valence electrons. Once again, let's think about this. We already know it's going to be so much easier for chlorine to steal an electron from somewhere than it is for it to get rid of its 7 valence electrons, okay? So it's going to want to steal 1. Magnesium, it's got 2 valence electrons, but it wants to have 8. Is it going to be easier for magnesium to steal 6 valence electrons, or is it going to be easier for magnesium to give away its 2 valence electrons so that it now gets rid of that outermost energy level and drops down to the energy level below it, which has a full octet? It's going to be easier for it to give away. So that's what's going to happen. Chlorine is going to steal that 1 electron from magnesium. And when it does, chlorine is going to be happy because it now has a full octet. But magnesium isn't quite so happy. It still has 1 valence electron to get rid of. So what's going to happen? Well, it turns out that, like in real life, okay, if magnesium is next to 1 chlorine atom, more than likely, in fact, it's a guarantee, there's going to be another chlorine element, chlorine atom around there too. So that's what happens. The magnesium will be next to another chlorine atom that wants its extra electron. So that chlorine atom will steal the extra electron from magnesium. Okay? So now the magnesium will have a +2 charge because it just lost 2 of its negative charges. So it has 2 excess positive charges. And each chlorine has a -1 charge. But they're happy. And so the +2 charge on magnesium will be attracted to the negative charges on the chlorine, and that will form an ionic bond. And it also explains why when magnesium and chlorine interact, 1 atom of magnesium will react with 2 atoms of chlorine to make magnesium chloride. And that right there is showing you that it's 1 magnesium bound to 2 chlorines. Okay, so that's the end of my presentation. I know that it was long. If it's confusing to you, please reach out. I'd be happy to explain it, maybe, in real life on chat or on a Facebook Live where you can ask me questions and I can clarify directly. That would be helpful. I think that I'm going to take the information from this presentation, put it in a blog post, and then add some links to hands-on activities that I use in a co-op setting that just really help students. I mean, it can just be so hard. You're up there talking to the student or they're reading their textbook and it's very abstract. But if you can find a way to model it, especially with pieces of candy to act as the electrons or something like that, and the kids can actually move the valence electrons and watch, what happens, it just makes things make a lot more sense. So I hope that was helpful to you. If you ever have questions, please reach out to me and I'll talk to you soon.